I was doing work using kind of gradients to optimize structures, and then people use gradients to optimize everything. So actually, I kind of think of them as similar works. But I'll talk to you today about some of the experiments we've been doing in learning latent structure for language. So let me begin by saying that this work is all work done by my students. So several of my grad students and undergraduates. And we have a little group at Harvard. We're trying to do work in these areas. A lot of the work today I'm going to show is from my grad student Yoon Kim. I guess it doesn't work up here, so I'll give him credit. And some of the more applied work is done by other students in this group. And a couple of my students are graduating, so please take them and give them jobs, et cetera. So let me first begin by giving a preface on just the core ideas that I'm going to refer to over and over again in this talk. For a lot of people in these rooms, these ideas are now second nature. But I think most of them are still pretty recent, so I want to go through them in detail. So the first kind of core idea is the work in neural machine translation. The base model we'll refer to again and again is a straight sequence-to-sequence model. Here we start with a sentence such as over the line. We then encode that sentence using an encoder network. Throughout the talk, I'll mostly use this in blue. This network is a recurrent neural network that produces a hidden state representation at every point in time. And then finally, a context vector in yellow, which is supposed to represent in a fixed dimensional representation all the information that occurred in that sentence. We then take that vector and we combine it with a red decoder RNN. At every time step, the decoder RNN hidden state is combined with the context vector to predict our next word. We continue running this process, feeding in the word in an autoregressive fashion to predict the next word in the sequence onward. When you build this model, if you build it big enough, you can get reasonably good performance in machine translation. Now, mathematically, the model looks like the following. We have an encoder network, which we'll write as just an RNN applied to each one of the hidden states time by time. We'll write these hidden states as h superscript x. And then we'll have a context vector c that will represent the final hidden state of that network. We'll then feed this representation into our decoder to produce each of our hidden decoder states, which will be used to predict the next word along the process. Now we can then extend this model to an attention-based neural machine translation system. Here we have exactly the same structure for our encoder, and for all my examples, exactly the same structure for our decoder. But then we're going to use the decoder hidden state to get a context vector that's specific to the current position in translation. So here, given the first decoder hidden state, we'll use that as a query to get a distribution over all of our source vectors. That distribution will be used to weight each of these vectors and to take a convex combination or an expectation to produce a weighting of each of the original RNN hidden states. They'll then be smashed down to a single vector, and that will be the vector we use to predict the next word. You can continue running this process in exactly the same manner to produce each of the words in our sentence. Now, for the purpose of this talk, we'll use roughly the same encoder structure, the same decoder structure, but really focus in on this attention. And we're going to talk about different mechanisms that you can use for that attention structure and some recent works on the process of using attention. Now, of course, I'm interested in generation, but these similar mechanisms are now really widespread in NLP, and in fact seem to be the kind of main tool in everything going on in tasks like question answering or generation or reading comprehension. And in many ways, attention has replaced kind of explicit latent variables for many of the problems we work on in this area. So one very simplified version of question answering is this task, where we're given a knowledge base of 6 sentences. Greg is a frog, Brian is a rhino, Lily is a rhino, Greg is green, Brian is right, and John is a frog. We can then represent each of these facts as a vector, and then take in a query, such as what color is Lily? That query then uses attention as a way to do our selection. So what would normally be done in just a latent variable here is now done in this differentiable manner, where we get a distribution over each of the things in our knowledge base. We use that distribution to get a new context vector. That vector is then used to update our original query, to query again, produce a new context vector, and update the query. And in some ways, by doing this process, we've now constructed a kind of latent path through our knowledge base, where we look at the facts of Lily is a rhino, Brian is a rhino, and then Brian is white. And we hope that that can then be used to produce our answer to this question, that is white. Of course, these aren't really latent variables. We don't really have a full probabilistic model here. We have this kind of soft approximation, where at every stage, we weight each of the different facts based on this distribution. We hope that it kind of makes hard decisions along the way or makes harder decisions along the way, but we've really kind of just approximated it with this process. OK. So, oh, yeah.
Sorry.
Sure.
I'm not sure that I understand the distinction that you're drawing. In other words, because you were saying, right, you're defining a distribution in each stage.
Yeah.
And then you said, but it's not a latent variable. So is it because it's not a proper probability distribution? Or I guess you're saying it's an approximation? Can you just explain better?
Yeah, absolutely.
This isn't just a probabilistic process.
Yeah, so probabilistic processes are wonderful because you can use them to make probabilistic queries. You could ask for, say, a marginal probability of a certain aspect. You could say, what would happen if this was on? Give me the marginal probability of this, right? We don't have any ability to do this here. We don't have a true graphical model. We can't kind of run that inference in that way. We can only run it in this kind of forward manner, where we force a probabilistic interpretation, but we don't really have a way of kind of doing traditional inference, if that makes sense. OK, cool. Any other questions about the kind of structure of the talk so far? Yeah?
So from a practical point of view, is there any downside to this? This sounds like it's got, the benefit of theft over honest oil, which, in my mind, is a good thing.
Absolutely. And I am actually a wide user of these types of models, and I think they're fantastic. And in fact, actually, there's a lot of work kind of even going beyond this model here and just saying, why do we even have recurrent neural networks? Let's just have attention all the way through. And those models, if you have kind of Google scale computation, can work pretty well. The argument, though, is that there are becoming more and more issues in deep learning where we kind of yearn for the kind of old-fashioned niceness of probabilistic models. Either we want to impose priors, or we have little data, and where we can't really hope to just learn everything, including these internal parts, kind of end to end. So some of the talk today will be about trying to kind of downscale some of these models to kind of allow us to kind of insert these assumptions more so. Yeah. Cool. So yeah. So actually, let me say the following. So I think that's a really good point. I don't want to say that these are the wrong method. In fact, a lot of the work that my group does is using various forms of attention for various problems in natural language processing. And the kind of center of our work is an open source toolkit that we built called OpenNMT. And it re-implements all these ideas of machine translation in an open source framework. We do this in collaboration with a company called Systtron, which is a French company that works on machine translation. And they use this kind of open source toolkit to provide translation services. So we now have 3 versions of this, one in PyTorch, one in LuaTorch, and one in TensorFlow. We have about 2,500 stars in GitHub, so it's getting a wide use. And it's a completely open source and transparent product. Actually, most of our contributors now are just kind of random people, many in Europe and in China. So a lot of our time is kind of just taking these pull requests and adding new features. Recently, we've been developing a lot of new aspects to the toolkit, including a focus on a method I won't be able to talk too much today, but is known as the copy mechanism, which is really useful in tasks like summarization and other types of natural language generation. We've also been implementing this recent work I just mentioned from Google this summer called the transformer model, or attention is all you need. And our kind of aim is not to be as feature-rich as other toolkits, but to provide a really minimal interface that's useful for research. So the whole toolkit is, I think, around 2,000 lines of code. Everything is, we try to keep well documented and well extendable. The other problem we work on is natural language generation. So we introduced some of the first models for neural abstractive summarization. So these are models that try to take in a source sentence in this case and produce a shorter sentence. This uses extensions upon the neural machine translation structure I've shown so far. So given a sentence like Russian Defense Minister Ivanov called Sunday for the creation of a joint front for combating global terrorism, we'd like to output Russia calls for joint front against terrorism. So use the ability of these models to generate words as a way of getting out of the kind of constraint of just being able, or just being forced to use the direct words from the source sentence. And there's been a lot of interesting work from other groups, particularly this year, on extending these models to full document summarization. Another area we've worked on recently is kind of bizarro OCR. So in this paper, we built a data set of mathematical images and the corresponding LaTeX. We scraped these from the archive to get a large set of images and the underlying LaTeX itself. And we use a two-stage attention mechanism to allow us to look over the image, find an area that we think is important for the next symbol, and then use a find mechanism to try to pick out the exact place in the image to generate. And by doing so, we're able to get really high accuracy at reproducing LaTeX output. And what's fun about this task is that no one writes LaTeX in the same way. It's basically a mess. And so while you don't do a very good job of reproducing what people do, for this task, you actually can generate the image and compare your accuracy on how well you reproduce the original image with your markup. And on this data set, we're able to get about 80% accuracy on that task, compared to about 15% exact match accuracy for systems people are selling that are kind of commercial rule-based systems. And then a task we've been interested in more recently, which I'm happy to talk about, but I won't go into too much detail, is generating from structured data. So this was a shared task that just finished called the E2E Natural Language Generation Challenge. Here you're given meaning representation, such as facts, the Golden Palace, it's a coffee shop, it's fast food, it's cheap, and it's in Riverside. And then you're given a sentence describing that data. So a coffee shop located on the riverside called the Golden Palace, et cetera. And so you can extend these methods to work with tabular data and to be able to copy facts from these tables in order to produce these reference outputs. And doing that with a couple more bells and whistles, we were able to get first place in kind of automatic scores on this data set using kind of our open source system. I will caution, though, that when they did human evaluation on this type of results, they're seeing that there's not too much of a win from using kind of really deep end-to-end systems. And so while we're seeing kind of progress on these metrics, it's not totally clear that these can replace other types of ways of doing natural language generation. OK. But what I want to talk about today is some of the more kind of theoretical work we've been doing in this area. I'm going to talk about two recent papers that look at how we can use end-to-end neural systems as a way of getting at some of the structural properties of language. And the hope here is to use something like attention as a way of getting out kind of representations of what's going on in a sentence in such a way that we can kind of manipulate and change the structure of what we produce. So the first work is work from this summer on structured attention networks. This is with my student Yoon Kim, Carl Denton, and Louis Huang. So there are a lot of images in neural models that show kind of where attention is looking as you go, either looking within image, here doing image captioning, or say looking over speech. So here is an end-to-end model that points to different areas in spectrogram using the model that we showed earlier. And I want to be a little more formal with what I mean when I say it's looking at these areas and look at actually what we are showing when we do attention. So here we're going to write the source that we're interested in as vectors x1 through xt. These will be the memory banks of things that we want to attend to. And then we'll have a query queue, which will say what we're looking for. We're then going to introduce a latent variable z, which will say where we're looking at in the model. And our attention distribution is the probability of this variable z conditioned on the query and the source. The thing we output, the context vector, which I've shown in yellow, will be c. And that's simply the expectation of our memory when we have our query queue. Okay? And as I was saying earlier, the requirements of this model is we need to be able, within our neural network, to compute this distribution over where we're looking at. And then we need to backpropagate over that distribution to update our parameters. This is the way we're able to learn attention as part of the model itself. So the way we do this is we compute the attention using a SoftMax function, which projects from our query and our source to a distribution. And we backpropagate because this function is soft and differentiable. So this is what it looks like. For translation, we'll say our vectors are x1 through x4, and our query is q. Our distribution is this heat map here, probability of each location. And then our softmax makes that a distribution. We then take an expectation to get a context vector in yellow, and we use that to produce our next word. Now, of course, each step in that process was differentiable, so we can just backprop through this to update our encoder states. Now, what if we wanted to do the same thing, but we wanted to have multiple words be able to be selected by the model itself? So instead of just saying we're going to have a distribution that says there's likely one place, let's say we wanted to allow multiple positions to contribute to our output. So instead of having a softmax, you can instead have just a sigmoid at each of those positions. You'll have basically what would be equivalent to a Bernoulli random variable. Either you take that position or you don't. And you use that to determine 0 or 1 for each position. This will then give us the probability of each of these choices. Now we have a random variable at each location, 1 through 4. And we use that random variable to decide what gets sent through the model itself. Okay? So what we're going to do in this work is we're going to say, well, those are two options. One option is to have a kind of single source picked by the system. The other is to have any one of the positions be chosen independently. But there's a whole wide range, a whole world of different ways that you can select this distribution. And it could be any distribution you wanted between each of these z1 through zt. So we're going to insert basically into this spot an arbitrary graphical model that will allow us to choose what we'd like to utilize in attention. And then we're going to try to utilize that in an end-to-end way to learn that structure as we go. So what does this look like? So instead of now having each position selected independently, we're going to allow there to be correlations between the outputs of the selections that we make. So instead of saying you can only pick each x1 or x2 or x3 or x4, or if you kept to select from all of them, we're going to allow us to have structure here to determine if we're going to pick one word, we might want to pick the other one as well. So we're going to consider all the different possibilities over here, all the different ways you could select words, and we're going to parameterize that with a distribution. So our distribution here will consider all the different possibilities for how we might choose from the words we're interested in. So here's one choice we might make. We pick the middle two words. Here's another. And depending on which we take, we'll end up with a different context vector, which will get used for our output. Cool. Any questions about the motivation? Yeah?
Are you still generating one word at a time? When you're selecting more than one word?
Yeah, so we're not changing anything about our output. It's still just taking everything from here on over is exactly the same. All we're changing is what we actually look at to generate the next word.
What happens if you're, I mean, this is a 4-word document, but what if the distribution is like, instead of 20 words or 30 words?
Completely fine. So then it's a distribution over as many of those 20 or as many of those 30 words as you think might be useful for the next output. So to give you an example of one of the applications that we're going to talk about, one of the translation problems we're interested in is translating from a language like Chinese to English. So while the assumption that one word will output one word in English might make sense for, say, French, it doesn't make sense for Chinese, where there might be multiple characters that contribute to the next generated word. So in that case, you'd like to give the model the opportunity to attend over, say, a series of characters that are next to each other to generate the next English word in that case.
So
Yeah?
doesn't using a softmax allow you to distribute attention over multiple words?
Yeah, that's a great question. So while in theory that's true, if you think about how the softmax distribution actually looks like, it really discourages that, right? You can kind of find a point that kind of equally weights multiple words, but to do that, you really have to learn to balance like exactly the right values. I guess the softmax is kind of trying to push you in some ways to make a single selection, even though it's plausible to have others. Yeah. Cool.
Even before going
Yeah.
to the structured attention, have you noticed any like degenerate solutions when you move into the Bernoulli formulation for the attention? Like the network decide that it's better to have all the vectors around and later make a big
Yeah, so why don't actually, these are good questions. I'm going to just skip and I'll go back. So here's an example of the kind of things we'll see. So here's a problem where we're trying to translate from Japanese to English. What we're showing here is a kind of Japanese character to English language translation. And here's the attention distribution you'd roughly like. If you really were being true to the Japanese, you'd have multiple characters that would influence every output for the word. If you have something like simple attention, you do see that the model attempts to kind of balance between multiple things. And it's often able to balance between, say, two different characters roughly equally. But it's very hard for it to spread it out to 3 or more characters just from the structure of the softmax. Conversely, when you use sigmoid attention, this is the kind of Bernoulli interpretation, you see the opposite problem, where you see degeneracies where it really spreads things out all along the process itself. And it's kind of unable to kind of focus in on things because too many values are on independently. And you can think of what we're doing with structured attention as basically learning a smoother over these two distributions. Because we're able to model the transition probability between two things being on in a row, we're able to get a kind of smoother, although not exactly correct, attention for these distributions. So that's kind of the main pitch. And I think it gets to some of the questions people are asking. Cool. Any other questions? OK, let me go back. OK, so let me just give a little bit more pitch about what we're doing in its own. So there's been a lot of work that looks at how you model these structural relationships on the outputs of neural networks. So a lot of work on kind of deep conditional random fields where you say, I want to predict the output variables such that they have a certain structure. And these models, I believe, are still the state of the art for problems like neural NER. And this is tractable if you make certain assumptions about the relationships on the output, such as it looks like a first or second order conditional random field. And it's also easy to kind of backpropagate over these objectives. We've been doing it for 20 years in NLP. And this is roughly like what these types of models look like. Now, unfortunately, it's a little harder to build these structural assumptions into the neural network itself. So I won't go through the math in great detail, but it turns out that there's a lot of nice properties from having the structure in a conditional random field be at the output layer. The math simplifies greatly, and you get kind of much simpler gradients. It's a little trickier when you put it inside the network itself. You have to be able to kind of backpropagate gradients that you get at any possible output of the CRF to any possible input. And so what happens is, in order to compute the equivalent of a softmax for this model within the network itself, you have to actually run inference within the network. So you have to run forward backwards in order to compute the neural network forward pass. And then to run the backwards pass, you actually have to backpropagate through the forward backwards algorithm itself. So you have to get these gradients through the algorithm. So what happens is that in the process of computing attention this way, you run forward backwards to get each of these local probabilities of a given word. you use that to compute your attention vector. And then on your backward step, you actually run a kind of standard backpropagation through all the operations in forward backwards. And since these kind of classical algorithms just consist of a bunch of sums and times, all those operations themselves are differentiable, and you're able to compute these gradients. Now, in the work itself, we ended up having to implement a lot of this in a pretty low-level manner in order to do this. But with the kind of arrival of really nice auto-differentiation frameworks and really fast backpropagation algorithms, doing this has become much, much easier. And a lot of the people who went back and re-implemented our work in toolkits like PyTorch or DINET have found that they're able to kind of get around a lot of the issues we ran into even just a year ago. OK. So let me talk a little bit about some of the experiments we ran. So we implemented this in a general purpose way such that we can include this style of structured attention for many different networks. And we looked at experiments in translation, question answering, and natural language inference. So for translation, we implemented a standard encoder RNN. We use a very simple objective to get potentials in our conditional random field. And then we used structured attention in order to backpropagate over that. The key idea is that we only actually have 4 more parameters in the model. Our parameters only tell us the probability of a word being used and the next word not being used, a word not being used and the next word being used, and then the other kind of permutations of that. And then we worked on a Japanese to English translation data set. And these data sets traditionally use word segmentation as pre-processing. So they first determine the Japanese words and then use standard machine translation techniques. We're going to use structured attention instead to kind of act as implicit segmentation. And so what we found is that when we were working in a character-to-word setup, we actually get a little boost using structured attention versus the other 2 approaches. When we actually have a many-to-one problem, we see improvements on translation when we use this structured model versus using the sigmoid, the decision independently at each position, and then also using a standard attention model. When we do word-to-word, all 3 models roughly perform similarly. So when we have the one-to-one setup, the kind of analogy we've been using so far works. And I think I showed you these already. OK.
Does character-to-character translation from English to Japanese kind of make any sense? I genuinely don't know this question.
Yeah, good question. So everything we're doing is only on the encoder side so far. So if you want to translate from English to Japanese, you'd like to have a kind of variability on the output layer of the decoder. Nothing we've talked about so far has that impact. But you can imagine kind of ways you would take this general mechanism and use it for that type of, that part of the network itself. That makes sense.
Yeah, I guess following up on that, the question is, does the structured attention help as much in the case where you have like byte pair to byte pair?
When it's straight byte pair to byte pair. Yeah. Yeah, that's a really good question. I'm trying to think. I think it probably would. So there's no inherent reason why the byte pairs like align between the 2 languages, that they find the minimal representation. Like in theory, byte pairs should do like decompounding of German words, but I'm not sure they always like fully split the compound in exactly the same way English does. So having the kind of flexibility, I think, would be nice. Yeah. Yeah.
So it seems like you're replacing kind of soft attention over lots of words with a hard decision about attend to this word and don't attend to this other word.
So actually not. Everything we're doing is still soft. So you can think of regular attention as being a soft version of a categorical variable, so soft of selecting one, whereas we're a soft version of a distribution over segmentations. So we're just soft over a different set of variables, if that makes sense. So I'm sorry, this is a, so we're soft over these choices, right? And literally, mathematically, it's exactly the same. So we're soft over this exponential set of things. Yeah. Cool. Any other questions? Yeah.
Following up on that question from you about character to word translations, there are certain other representations of character to word translations between certain languages such as Chinese and English.
Yeah.
For example, you have pinyin representations.
Yep.
Can those be used to guide the structure description?
Yeah. So I think in general, I'm not making any claims about how you should do Chinese to English attention. The way you probably should do it is by pair encoding and a very big model. I think I just want to use that as an example to show kind of how you might think about these tools. Like we're kind of introducing a kind of different type of general purpose tool that you can put into a neural network, and it has different properties than a kind of standard method, or a standard attention method would have. Yeah. Cool. Yeah.
Do you have results for how well it does the word segmentation?
That is a great question. I don't have those results, but I think that's something we should definitely set up. I do want to say, people have done comparisons with how well regular attention does compared to supervised alignment models. So there are supervision of like language-to-language alignment models, and people have compared regular attention to that. And my understanding is that it doesn't perform as well as systems that are trained just to do the alignment. But it is kind of neat that it's able to learn something reasonable without getting any kind of like supervision on that particular task itself. Okay. Okay, cool. So let me just show two quick other examples which I think are pretty fun. So I mentioned earlier this task of kind of very simplistic question answering, where you kind of apply attention in multiple steps throughout the model. And I think for me, the thing that's a little bit frustrating about the way people are using it for this problem is that it's greedy. Depending on the first decision it made, it just moves ahead to the second and makes another decision, and then moves on to the third and makes another decision, which I think is fine. But we have ways of considering all these selections together and exactly computing attention over all three decisions in a way. So instead of kind of doing this greedily, our suggestion is we should think about this as a lattice and think about all of the different three selections you might make. And you can encode that as a conditional random field and then build it in to structured attention, where the attention is now over all three decisions simultaneously. So we literally encode all the pairwise edges that might occur in this graph. We then run forward backwards to compute the true marginals. We use those marginals to apply attention over all the selections itself. And for this task, we're able to replicate the same scores that you get roughly with simple attention. This data set is actually quite simplistic, so I think the greedy approach is maybe reasonable. It's only 3 decisions in a row. But what we do find is that the latent structure, the path that we actually find through the facts, is better than the one we found with simple attention. So we're able to better correct for selection mistakes that are made, and we learn kind of latent selection of facts that's better for this data set. I caution again that this is actually a relatively poor data set, and that there are kind of better question answering data sets, but these are just preliminary experiments. Okay.
Quick question?
Sure.
So what happens, is there a scaling problem? You're showing an example that fits on the slides. What if there are a lot more facts that you have to consider?
Yeah, so actually on this data set, it's only 3 facts. So there is a kind of limited area. I don't think there's inherently a scaling problem because of, yeah, I think you could roughly run this for as long as you wanted. I mean, the only scale would be it's going to scale quadratically in the number of facts you have. So you have to worry about that. But you could imagine a kind of faster way of doing that kind of calculation.
So it's scaling quadratically in the number of facts. We can see that with the pairwise thing.
Yeah.
And I think it's reasonable to think that, right, that the number of steps is limited. I'm just trying to match that up with a kind of inherent notion that inference is exponential.
Mm-hmm.
And maybe it's because this is propositional rather than first order, but again, it seems like something is missing here. From this
Sorry,
one.
did I claim that inference was exponential? Or
No, I
oh.
claimed that.
Oh, okay. So the main idea is that we're going to making all the same assumptions you would make for a kind of standard conditional random field. So because we're making the assumption that it's just pairwise here, even though there are an exponential number of possibilities, you can do inference in polynomial time. So we're going to be running kind of classical forward-backwards on this problem. It's going to scale quadratically with these relationships. Yeah, so that's kind of the key assumption we're making. Okay. Cool. These questions are great, guys. Thanks. Let me mention just one more application because I think it's cool, and then I'll get to the second half of my talk. So the last application we looked at was, oops, oh no, I lost my slide. Okay, I won't talk about it too much. The last application we looked at was natural language inference. So here's a problem of you're given two sentences, and you have to decide whether one entails the other, whether they contradict each other, or whether there's no relationship. This has become a kind of standard benchmark task in this data set called the Stanford Natural Language Inference data set. There's kind of been some work that suggests it would be useful to have the syntactic structure of the sentences in order to do this comparison. That if you knew what the main verb was or what the arguments were, that would help you determine whether one entails the other or not. And so a lot of people have used models where they first parse one of the sentences and use that as part of the features for making this determination. So it turns out that dependency parsing, a long-studied problem, fits all of the assumptions that we're interested in for structured attention. So we can simply embed a dependency parser as our attention model, where what we're asking the attention to tell us is, what do you think is the head word of every word in the sentence? In this way, we don't have to provide any parses. We can just learn the problem of natural language inference, but ask it to actually run a dependency parser internally in order to make decisions. When we do this with structured attention, we get a nice improvement on this task. The kind of enforcing these dependency structure constraints actually do better than just using a model with simple attention. At the time of this publication, this was still about a point lower than the state of the art. But this baseline simple attention model we're using is quite strong. And so we actually are seeing a little bit of benefit here from doing this. What we didn't find was that if we forced our attention model to agree with the true syntax, we didn't see that give us any kind of improvement. So we tried kind of pre-training on real sentences, and unfortunately that didn't help. But kind of allowing it to do its own thing, but forcing it to produce trees gave us a benefit. And out of this, you actually get kind of the trees this model was like learning to hallucinate. So these are kind of the attention trees from the model itself. And what we found in general was that they really fixate on the main verb. I mean, they're not great trees, but we do get some kind of one or two layer structure out of the model itself. And I mentioned this last work because there's been some interesting work since we published this on other methods for applying structured attention within systems for classification and for NLI. So there's really interesting work by Liu and Lapada where they do exactly the same method we're using for dependency trees, except they use a different type of conditional random field. This is known as a non-projective dependency tree algorithm. The details aren't that important. But the cool part is that it turns out this algorithm has like really nice structure such that you can backpropagate through it really fast. And so the code for doing this method is like maybe like 10 lines. So you just have to take a matrix inverse and then backpropagate through it, and you can kind of add structured attention with trees to your model. So I think that's really cool. And they get some really nice results on kind of long form classification. Various other people have been applying the tree-based attention to translation. And there's some other work that combines these ideas with hard attention to do some of the stuff you were mentioning before of like getting a fixed segmentation of a sentence as you go. And I should say, so far, results are mixed. I think I'm not going to claim that this is going to give you state-of-the-art for many problems, but I think it's an area that's worth exploring more. Yeah?
So one really interesting thing I think about this is that is the case where the instances where you're using this latent attention for for the examples where you get it right in the SNLI corpus and using a syntactic dependency parse as the attention gets it wrong. What's the difference between those two trees?
Yeah.
Because that seems like the really
Yeah,
cool part,
I think
right?
that's really cool.
There's some tree which is a better way of representing the structure for these very particular examples. That seems like an interesting thing to look at.
Yeah, we haven't looked too much at that part of the analysis. I think one argument might be that there are a lot of mistakes in this corpus, so they might just be wrong types of things, or we get kind of a pipeline error. But it would be interesting to see if they were actually like, it got the syntax right, but it didn't help it in the conclusion of the system. Yeah. Yeah.
Do you know how efforts to inject sparsity into the SoftMax fit into this?
Yeah. That's a really good question. Okay, so so there are a lot of methods that look into that. We've looked a little bit at some of Andre Martin's work on SparseMax. My understanding is that you can't really compute that type of SparseMax projection with structured forms. He's done some work, though, on various other kind of extensions. So these are methods where you try to force the attention to only be on a small amount of the possible input. And then I think there has been some work that looks at kind of annealing type approaches where you increase the temperature. I don't know what the results of that have been so far, but I think that would be an interesting thing to look at. Yeah. Cool. Yeah.
Have you thought about integrating the structured attention into a copy mechanism? Maybe with the idea of copying multiple words?
I think that's a really cool idea. We may have some students looking into it. I haven't gotten any results yet. Yeah, I think I've been doing a lot of stuff with copy mechanism recently. I think it's really helpful. As a research direction, it bothers me a little bit. Like, I think it would be really disappointing if a lot of NLP turned out that you just needed to like lexically copy exactly from one to the other. I worry a little bit that it's a kind of crutch or like I would really like to get around that issue with other ways. But it definitely works well. And I think this would, in combination, would work. Yeah. Cool. Yeah.
Do you also update the dependency parse model by your
Yeah. So yeah, again, I think I should have included some more slides here, but because it's attention, we're backpropagating through the inference step into the parameters of the dependency parse. So actually, the dependency parse tree is learned entirely end-to-end with the rest of the system. And so I should give my student a little credit here. So this is actually running kind of Eisner inside-outside algorithms within a neural network system and then backpropagating through that. So it's kind of, algorithmically, it's kind of interesting to do that. Yeah.
Sorry, so I want to just ask you why you feel maybe negative on the copy mechanism.
Why I'm negative on copy mechanisms, yeah.
For some applications, it seems natural. For example, you're generating things from structured data, and then sometimes you're actually just doing some stuff. And so in that case, the copy mechanism is perfectly natural. And so maybe you're talking about other applications.
So I should say that we're using copy mechanisms super widely. We use it for this work. We use it for summarization. There is so much interesting research in NLG about this kind of question of what words you choose to output on the target side. So whereas I agree that for doing the kind of silly summary task we're working on now, where most of the time you just say the same thing from the source, it makes sense. But I'm really excited about like all the phenomena of language where you don't say exactly the same thing. So like metonymy, Russian Defense Minister Ivanov, you'd really like to output the word Russia. That's like a natural way of summarizing it. But copy mechanism is never going to get us there, right? And so I think what's really exciting about kind of the ability to generate arbitrary words is we can represent these phenomena that go beyond kind of just selection. So that's all I'm saying there. Okay. Okay, I have about 10 minutes left. I want to talk a little bit about my last work because I think it's pretty fun, and I'd be curious to get some feedback. And it's a kind of a very different style. So this is work on adversarially regularized autoencoders. It's with Jake Zhao and Kelly Zhang at NYU, and Yoon Kim, who's my student. And so one problem that really fascinates me is how we can kind of control the structure of the generations we produce. So I'd like to be able to kind of manipulate outputs to make a sentence funnier or shorter or more formal, et cetera. And this summer, there's been a lot of interest in this problem of kind of trying to output sentences of a different type. And I think the reason there is because we're all jealous of people in vision. And there's just been these like startling results, or startling to me results at least, of people being able to manipulate images to kind of take image and change the gender, change the age, change the facial expression. And so I'd like to be able to do similar things with text output. And the task that's been proposed for this is called unaligned text style transfer. And so we're given k different data sets that are not aligned. So there'll be one data set of positive examples, one of negative examples, but they're not the same. And we want to minimally map one sentence from one attribute to another while preserving the structure. So given a sentence like the movie was an excellent showcase, Ben Affleck and Matt Damon had tremendous chemistry, we'd like to produce the movie was a terrible mess, Ben Affleck and Matt Damon had no chemistry. That's kind of the dream. Well, that's not the dream. We want to do much other things, but this is where we're going to start. OK, and so the main mechanism people have been using for this in vision are generative adversarial networks. I won't have too much time to go through the math here, but roughly the idea is they're trying to solve this min-max problem with two networks. One is a generator that maps from noise to structure, and one is a discriminator that takes in two structured objects and tries to determine which one is real and which one is fake. Everything is trained together to produce these two output models. And the end goal is to be able to kind of take in various noise sources and output realistic objects. And so for images, it looks like this. We have a true distribution down here to the left, and we have a noise distribution to the right. We'd like our generator to go from noise to an image. We'd like to have the discriminator try to determine what's real and fake. We play this game to try to fool the discriminator. And with enough grad student search and blood, they get these models to roughly work. The problem is that no one's really gotten this model to work for text. There has been a lot of interest in this problem, but I think there's been some hurdles. And the hurdles are quite simple to understand. The problem is that you can do this part of the discriminator in exactly the same way. But when you map from noise to a generated text sample, you hit upon this point of non-differentiability. It's very important that our outputs in text be actual words. But if you make actual hard decisions about the words themselves, you lose the ability to backpropagate from the discriminator through the generator. So particularly this part of the gradient gets messed up when we have text examples. And so you can't just use exactly the same mechanisms with text in order to train your generative adversarial network. And so we've been kind of stuck on this point here. Now, I should say there's been a lot written about how you might get around this issue. So one is to use policy gradient or like reinforcement learning style approaches to just say it's non-differentiable, so we'll use RL. And the other has been to consider soft approximations. So basically, instead of making hard decisions about your words, you output just distributions over the words you might have picked. It's kind of a similar idea to attention as a way to make it non-differentiable, or make it differentiable. But as far as I can tell, I don't think any of these have really convincingly gotten around the issue so far. OK, so we're going to take a slightly different approach, which is to say, if we could learn in autoencoder for text, if we could learn a way to map from text to continuous space, then we could do all of this work in that continuous space itself. So if we could learn a model that looked exactly like the first model I showed in this talk, where we have an RNN encoder that maps from text to continuous space, and then back from continuous space to that same text, then we would have this continuous representation in d dimensions that represents our sentence. But there's kind of a chicken and egg problem here, which is that we also can't do this. right? We can neither learn a good autoencoder nor can we learn a good GAN for text. And so we're just stuck with the discreteness of the domain. So the kind of solution proposed in this work is just to learn them simultaneously. So we're going to try to learn a text autoencoder that maps from text to continuous space out to text again, and a GAN that exists entirely in that continuous space simultaneously. So we're just going to alternate gradient steps between these two problems. So here's the GAN we're going to learn. So instead of sentences, we're going to work with encoded vectors. And our generator is going to work from noise to one of these encoded vectors. So the discriminator is going to work entirely in code space to try to determine whether this was a real encoded sentence or a fake encoded sentence. So here's the full model. So we have sentence, encoder, code, decoder, sentence. We try to make it as good as possible at recovering the original sentence. And then we have a GAN that maps from noise through a generator to code space, and then a critic or discriminator that tries to determine the difference. Okay. Now, this generator is pretty simple. It's just like a simple neural network. This is our big R and N. Okay? And the hope is that if this is simple enough, we're kind of restricting how powerful this part of the model can be. So the autoencoder can't really memorize exactly the sentences because it has to work together with this generator here. It's kind of a hand-wavy argument. I'm not super happy with it either, but that's the structure. OK. So let's see. Let me skip ahead a little bit. So it turns out that this GAN produces pretty reasonable sentences. They're reasonable enough that if you output enough of these sentences and retrain a language model on those outputs, you do roughly as well as running the same thing on a language model. So the way we did this is we just gave noise to the, we gave noise here and then output through here. So we take this path through the GAN and get sentences in there, and then we use those to retrain a language model. And the hope is that if they're natural enough, or if they capture enough of the structure, that you could retrain a simple language model just in those sentences as a way of capturing kind of how well it captured the distribution. This is roughly similar to some of the methods they use for vision, such as an inception score, et cetera. OK. OK, so the original task we were interested in was how do we transfer a sentence from one style to another. And to do this, we're going to do the following. We're going to add in a classifier that tries to make it, or the job of the classifier is to try to determine whether a coded sentence was positive or negative. So its job is to look at the code, determine whether it was positive or negative. So the full model looks like this. We're going to take in a sentence, encode it into this code space. We're then going to have two decoders, one that tries to output only positive sentences, and one that tries to output only negative sentences. We're going to have a classifier that tries to determine from the code space whether it was positive or negative. Okay? And then we're going to train against that. So the job of the encoder is to fool this guy and generate a code here. So the hope is that strictly in continuous space, if we can fool this classifier and have different decoders, we can take in a positive sentence, output it either in the same way as a positive or as a negative in this way. So without having training examples, but only having this guy to fool, we want to try to make that switch. Okay? And so doing this strictly in continuous space, we get relatively interesting results. So our model is ARI, and this is a model recently proposed by MIT. So given a sentence like, we came on the recommendation of a bellboy and the food was amazing, we output, we came on the recommendation and the food was a joke. Comparatively, we see, we went on the car of the time and the chicken was awful. Okay? So both of those successfully map from a positive sentence to a negative sentence. But the argument is that learning kind of in this way, we kind of keep most of the structure of the original. So this is a little bit difficult to evaluate. We did some automatic evaluation where we look at how often we transfer, how close we were to the original, and what our kind of perplexity was of our output. We also did some human evaluation where we asked people to say how natural and how similar the sentences were. So we see pretty high scores from our model on naturalness. I think it's 3.8 out of 5, and it gets about 74% transfer of the actual sentiment of the sentence. And then finally, we did larger K experiments. This is a topic data set. Given a sentence, a music sentence, do you know a website that you can find people who want to join bands? You get a science sentence of, do you know a website that can help me with science? Or a politics example, do you think that you can find a person who is in prison? So roughly capturing the same kind of syntactic structure, but changing the topic of the words. Cool. OK, so I think I'll end there. I do want to note that I'm also not super happy with the formality of this type of work. It's kind of a first hacky attempt. But I think this is a really interesting problem, and that we'll see kind of cool work going on in this space. And there's a couple works at ICLR that try to do this method, but to do translation with unaligned examples. And we're starting to see some kind of cool results of like French to English translation without actually having to have aligned sentences. Cool. Thanks.